If you've been following AI research lately, you've probably noticed a quiet but massive shift happening under the hood. The attention mechanism that powers almost every large language model is hitting a wall. We're talking about quadratic scaling, massive KV cache footprints, and hardware that's struggling to keep up. And yet, a new class of architectures is stepping in to fill the gap: state-space models. Specifically, the Mamba family. Today, we're going to break down exactly how they work, why they're being adopted so fast, and what the latest research says about their future. To understand why state-space models matter, we first need to look at what they're replacing. Transformers rely on self-attention, which computes pairwise relationships between every token in a sequence. That's incredibly powerful for capturing long-range dependencies, but it comes at a steep cost. The computation scales quadratically with sequence length, and during inference, you have to store and update a key-value cache for every token. That cache dominates memory usage, especially on long contexts, and it forces hardware to constantly shuffle data instead of doing heavy compute. GPUs are built for matrix multiplication, not memory-bound sequential access. So researchers started asking, can we keep the expressiveness of transformers while dropping the quadratic bottleneck? That question led back to a decades-old concept from control theory: state-space models. In simple terms, an SSM maps an input signal to an output signal through a hidden state that evolves over time. In the continuous time formulation, you're working with a system of differential equations where the hidden state is driven by the input through projection matrices A, B, and C. It's essentially a recurrent structure, but formulated as a continuous system. The problem is, neural networks don't natively process continuous signals. They need discrete steps. So the breakthrough came when researchers figured out how to discretize these continuous equations using standard numerical methods like zero-order hold or bilinear transformation. That gives you a discrete transition matrix that updates the hidden state at each time step, just like an RNN. But here's where it gets interesting. Traditional RNNs and even LSTMs struggle with long sequences because gradients vanish or explode, and the fixed transition matrix doesn't adapt to the input. Mamba solves this with a single, elegant addition: selectivity. Instead of using a static transition matrix, the model learns input-dependent parameters. At every time step, the discretization parameters are dynamically computed from the current input. This means the model can choose to forget irrelevant information, retain critical context, or skip over noise. It's still linear in complexity, but now it's context-aware. That selectivity is what lets SSMs handle long sequences without the attention bottleneck, while staying competitive on tasks that require fine-grained token interactions. Of course, linear recurrence has a computational downside. If you process tokens one by one, you can't parallelize training, which makes SSMs slower to train than transformers on modern GPUs. The solution was the parallel scan algorithm, adapted from parallel computing. By restructuring the recurrence as a prefix scan, you can compute the entire sequence in logarithmic time on GPU hardware. It's a clever workaround that preserves the linear inference complexity while giving you training speeds that rival attention-based models. The trade-off is that the implementation is more complex, and the memory access pattern is less predictable than standard matrix multiplication. But for long context workloads, the throughput advantage is undeniable. The research landscape is moving fast. Mamba 2 introduced a hybrid attention mechanism that selectively applies attention only to a small subset of tokens, blending the best of both worlds. Meanwhile, researchers are exploring mixing SSMs with mixture of experts, using the SSM backbone for long-range context and routing specialized experts for domain-specific reasoning. There's also active work on improving the training stability of selective scans, optimizing the discretization step for better gradient flow, and adapting SSMs for multimodal and vision tasks. The consensus so far is clear. SSMs aren't replacing transformers everywhere, but they're becoming the go-to architecture for long context, low latency, and memory-constrained deployments. If you're building systems that need to process thousands of tokens efficiently, or if you're just curious about where the next generation of language models is heading, state-space models are worth paying attention to. The hardware efficiency gains alone are going to shape how we deploy AI at scale. I'll link the key papers and open-source implementations in the description, so you can dive into the math and experiment with the code yourself. If you want me to break down the parallel scan algorithm step by step, or compare Mamba directly to RWKV and Hyena, let me know in the comments. Thanks for watching, and I'll see you in the next one.